Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome to OP's Math e-Pathshala. Thanks for watching. Please subscribe, like and share. Welcome.
Hi friends. Hi friends. Hello. So today I came here to talk about two important tests, irreducibility tests, which are very much useful to check the irreducibility of polynomials over fields. And these tests has been so it seems to be more important in our PhD entrance tests like CSIR net, NBHM, TIFR. So these irreducibility tests can be viewed in terms of beautiful examples. So I shall explore some beautiful examples which are helpful in understanding this test. Now first of all I need to consider the definition of irreducibility of a polynomial. So a polynomial fx is said to be fx belongs to the polynomial ring capital Fx over the field f. It is said to be irreducible over the field f over the field f if fx cannot be factored into the product of two polynomials gx hx, where gx hx is in the polynomial ring fx, where something went wrong. Sorry. So yeah. So where 0 less than degree of gx, degree of hx is less than degree of fx. Yeah. Now it should be noted that uh, the definition what we have considered, uh, it concerns the concept of irreducibility over a field f, not just the concept of irreducibility itself. That is, it is irreducible over a field f because, for example, if we consider the polynomial x square minus 2 over q, then it is irreducible over q. But this polynomial is reducible over the field of reals. So that means the irreducibility depends on what the field we are considering. So this should be remembered each time. Whenever you are considering a polynomial over a field f, so you should remember the field. Okay. And for this reason, a polynomial can be defined as irreducible over the field f if it doesn't have any root in the field f. Okay. Now the test of irreducibility by finding these roots will work good for quadratic and cubic polynomials. So the test of irreducibility by finding zeros, or one can say roots of the polynomial, this will work good for quadratic and cubic polynomials. field having small number of elements over fields having small number of elements. But it will not work good for large fields, and that is why we need to have some criteria at our hand to determine irreducibility of polynomials in fx. I must note down the irreducibility test for quadratic and cubic polynomials. So the theorem is, so a polynomial fx belongs to capital Fx of degree, suppose 2, or we may suppose the degree is 3. A polynomial fx of degree 2 or 3 is reducible over a field f if and only if it has a 0 in f. So this is an interesting criteria to test irreducibility of a polynomial over a field f which is of degree 2 or 3. And yeah, so now the next theorem that I shall state is for the field of rational skew, and this theorem deals with the polynomials over the ring of integers. The theorem is, if fx belongs to zx, that is fx be a polynomial with integer coefficients, then fx factors into a product of two polynomials of lower degrees R and S in the polynomial ring Qx if and only if it has such a factorization with polynomials. Factorization with polynomials of the same degrees in the polynomial ring Zx, that is over the ring of integers. So if fx be a polynomial with integer coefficients, then fx factors into a product of two polynomials of lower degrees in Qx if and only if it has such a factorization with polynomials of the same degrees in Zx also. And using this theorem, you will have an interesting corollary. By the use of this corollary, you can deal with some examples of polynomials, whether these are irreducible or not, over the ring of integers and over the field of rationals. So the corollary will be, now let us suppose that fx be a polynomial with the leading coefficient 1, that is x to the power n, a n minus 1, x to the power n minus 1 plus a n minus 2, x to the power n minus 2 plus dot a1x plus a0, a1x plus a0. So this is a polynomial, be a polynomial with integer coefficients. Integer coefficients. And let us suppose that the constant coefficient is non-zero. Then if fx has a 0 in the field of rationals, then it has a 0 suppose the 0 is small k in the ring of integers which satisfies the property that this k will divide a0. So this theorem indicates that if fx has a 0 in the field of rationals, then it will have a 0 in the ring of integers, that is, it has a integer root which satisfies the property that this root will divide the constant coefficient of the polynomial. So that means you will search the root of this polynomial, integer roots of this polynomial amongst the divisors of a0. Right? And we notice that if a polynomial fx with integer coefficients and having leading coefficient 1, and if we suppose that the constant coefficient is non-zero, if it has a 0 in the field of rationals, then it must have a 0 in the ring of integers which divides a 0. That is, the possible integers that are zeros of that polynomial are those which are divisors of the constant coefficient a0. So this corollary has an important feature which will give you a beautiful possibilities to test the irreducibility of fx over q. For example, so we must illustrate an example which will be helpful to you. So for example, if we consider the polynomial x square minus 2, over the field of rationals. Now this polynomial is irreducible over Q, and it is known to us, but we shall check the irreducibility of this polynomial over the field of rationals using the corollary that we have stated above. So if we consider this polynomial, then we see that if we forcefully assume that yes, this polynomial has a 0 in the field of rationals. Assume that the polynomial has a 0 in Q in the field of rationals. Then by the above corollary, then it must have a 0 in the ring of integers. And not only that, this 0 will divide the constant coefficient, will divide the constant coefficient minus 2. So that means so this 0 in the ring of integers is possibly one of the divisors, which are plus minus 1 plus minus 2 of the integer 2. But if you intend to check the possibilities one by one, you will see that no one of these divisors will satisfy that it is a 0 of the polynomial x square minus 2. That is, if we put each of them individually to the polynomial x square minus 2, then the outcome will never be 0. Okay. So this is a very interesting example. Also, I can give you another example which is like the following. So example 2, that suppose that fx is x to the power 4 plus minus 2x square plus 8x plus 1, which is a polynomial that has been considered over the field of rationals. Now we need to check that this fx is irreducible. So we would like to check that fx is irreducible over Q. Over Q with the help of the corollary that we have stated above. Now suppose fx has a 0 in Q. Now since fx has a 0 in Q by our assumption, then by the above corollary it must have a 0 in the ring of integers. 0 in Z. And not only that, this 0 will divide the constant coefficient 1. And which indicates that the possible zeros, integer zeros, will be one of the divisors. Either it is 1 or minus 1. But if we put 1 or minus 1 to the polynomial fx in place of x, then we will see that f1 will be 1, 4 minus 2, 1 square plus 8, 1 plus 1. So this is 8, which is not equal to 0. And if we put minus 1 in place of x, we will see that it is minus 8, which is again not equal to 0. So this gives you a contradiction. And this contradiction will conclude that this fx is reducible over Q. So with the help of this corollary, you can easily check that a polynomial over a ring of integers is irreducible over the field of rationals or not. So this is an interesting test that you must consider for your exams. Next one is due to the famous Eisenstein criteria to check the irreducibility over the field of rationals. So what is the statement of the criteria? So this is Eisenstein criteria. For irreducibility. So this is also a very familiar test of irreducibility of polynomials over the field of rationals. And you will see that this test is very much easy to handle. But one thing that I must specify, that the choice of the prime is not very much handful to us, because sometimes it will work, sometimes it will not. So let us first state the Eisenstein criteria for irreducibility, which is, let us suppose that P be a prime. So you need to choose a prime first, keeping in mind the coefficient of the polynomial that you have considered. So suppose that fx is the polynomial a n x to the power n, a n minus 1 x to the power n minus 1, a 1 x plus a 0, which are, so the coefficients are in integer, with the conditions that a n is not congruent to 0 modulo p. That means that p, that prime, will not divide a n. that prime will not divide n, this the leading coefficient of the polynomial, but ak will be congruent to 0 mod p for all k less than n. That means except n, all the coefficients must have a factor p. That is, p divides all other coefficients starting from an minus 1, an minus 2, a1, a0. These are all divisible by p. And the last condition is the a naught, that is the constant coefficient, will never be congruent to 0 but modulo p square. So these are the conditions the Eisenstein criteria has, and if a polynomial will satisfy these conditions with respect to a prime p, then the conclusion is that fx is irreducible over q. So the conclusion is fx is irreducible over q. So in this test, if we consider this test for irreducibility of polynomial with integral coefficients, so our first goal is to choose a prime p keeping in mind the coefficients of the polynomial, because we need to check the three conditions. One is whether the prime that we have chosen divides the leading coefficient n, this one, whether the prime p divides all other coefficients n minus 1, n minus 2, a1, a0, and also we need to check that the integer p square, does it divide the constant coefficient or not. If the prime will satisfy these three conditions, then we can conclude that fx is irreducible over q. Now let us again recall that we have already seen in the previous discussion that the polynomial x square minus 2, it has been checked that it is irreducible over q. Now we need to check this irreducibility of this polynomial in terms of Eisenstein criteria of irreducibility. And for this reason, we need to carefully check the coefficients of this polynomial. So this polynomial can be represented as x square plus 0x minus 2. So the coefficients are 1, 0, minus 2. 1 is the leading coefficient. So keeping in mind these coefficients, we first see that the prime may work for these coefficients too. And the fact is that it is indeed, because with respect to this prime, we will see that these two will not divide the leading coefficient 1, but it will divide 0, it will divide -2. And the second thing is that, so this satisfies the two conditions, and the remaining one is that now we need to consider the 2 square, that is 4. So this 2 square equal to 4. Now 4 will not divide the constant coefficient. So thus, in that case, this prime works good. And the conclusion will be that x square minus 2 is reducible over Q by using Eisenstein criteria. Now I shall stop this lecture here, because in the next live session I will talk about more examples to show that how to deal with the problems using this Eisenstein criteria and the corollary that we have already discussed for 2 examples. And in the next session I will also call another irreducibility test that can be considered for your exams. Although this test is not in your syllabus, so in the next session I will talk about the new irreducibility test, and I shall illustrate some good examples that will work for our exams. Thank you.